Welcome to the grand finale of our Database Internals Explainer series. Today, we're putting everything on the table, looking at heavyweights like PostgreSQL, MongoDB, Cassandra, Redis, and DynamoDB. Now, we casually throw around the word database to describe all of these, but the truth is, they make wildly different engineering trade-offs under the hood. To truly understand them, we have to look right past the marketing buzzwords and examine the actual fundamental mechanics that make them tick.
So, let's dive right into it. Instead of introducing some brand new, isolated concept today, we're going to take absolutely everything we've learned over the last 6 episodes and use it to answer the ultimate, practical question that every single developer faces. Which database is actually right for your project? We're done guessing. Today, we're using solid engineering principles to make that decision.
Here's our roadmap for making sense of this chaotic landscape and tying together everything we've built. We'll start with a quick recap of our database toolkit, pit B-tree against LSM-Tree engines, and explore document and key value stores. Then we'll map all of this out on a grand comparison table and wrap up with a 5-question framework to guide your next architecture choice.
Section 1. The Database Toolkit Recap. Let's briefly look back at the analytical toolkit we've spent our last 6 explainers carefully constructing.
Think about the journey we've been on. We started bare metal with pages and the write-ahead log, moved up to strict ACID guarantees and query execution, and then scaled out with indexing, replication, and sharding. What's truly remarkable here is that these 6 concepts aren't just academic theory. They are the exact lenses you can use to evaluate literally any database in existence. Every single database out there is just a different set of engineering answers to these 6 specific areas. Because you now understand these foundations, you can confidently evaluate databases that haven't even been invented yet.
Section 2. B-tree versus LSM-Tree engines. Building directly on the foundation from our very first episode, let's tackle the most fundamental storage engine decision you'll ever face.
This brilliantly illustrates the core divide in how we store data. On one side, we have B-tree engines, which power heavy hitters like PostgreSQL and MySQL's InnoDB. Think of a B-tree like a meticulously organized filing cabinet. Every time a new document arrives, you carefully file it in its exact correct place immediately. Finding anything later is practically instant, giving you excellent read performance and mature ACID transaction support. But the physical act of filing? That takes time, especially when you're getting hit with random writes. On the flip side, we have LSM-Tree engines, used by systems like Cassandra or RocksDB. Think of an LSM-Tree as the inbox tray sitting on your desk. You just drop new papers on top, instantly, no matter how fast they come in. This gives you absolute lightning-fast, massive write throughput. But the trade-off is that reading is slightly slower because you have to search through a less organized stack. And occasionally, someone has to sit down and reorganize that entire tray, a background process called compaction, just to keep it searchable over time.
Section 3. Document and key value stores. Now let's apply our engineering lenses to some specialized tools where the underlying mechanics get really fascinating.
Let's use MongoDB as our prime example here. People often describe it as fundamentally completely different from something like Postgres, but through our engineering lens, it's simply a different set of trade-offs. MongoDB is a document database, meaning it stores data as flexible, nested, JSON-like documents. This is an absolute lifesaver when your data naturally varies in shape or evolves rapidly. You're basically trading away strict relational consistency for total schema flexibility. But here's the secret. Under the hood, MongoDB's default WireTiger storage engine actually uses a B-tree-like structure. The real difference is the flexible data model, not some magical new storage invention. And hey, if this is the kind of content you want more of, subscribing takes 1 second and it genuinely helps the channel grow.
Next up, let's look at key value stores, specifically focusing on Redis. Redis is an in-memory data store. It is the absolute equivalent of keeping your most used tools right on top of your desk for instant microsecond access. It is unbelievably fast because it bypasses the disk entirely. But the trade-off is clear, right? You are strictly limited by how much actually fits on that desk, which is your system's RAM. And just like a physical desk, if the house loses power, whatever wasn't safely written down in the garage toolbox, our disk-based persistence, might be lost forever. Redis trades large-scale durability and massive capacity for extreme sub-millisecond speed.
Then we have DynamoDB, which fits perfectly into this key value discussion, but takes it to a massive disk-based horizontal scale. DynamoDB is actually a direct application of the concepts we covered in episodes 5 and 6. It takes the leaderless replication we explored to ensure the database stays available even when multiple servers fail, and it uses consistent hashing to spread that data across a globally distributed cluster. It purposefully prioritizes absolute availability and virtually infinite scale over the rich, complex queries you'd get from a relational database.
Section 4, the Grand Database Comparison Map. It is time for the ultimate payoff of this entire series. We are bringing all of these distinct technologies together into one unified picture.
Take a moment to really soak this in. This table perfectly organizes the chaos of the database market, showing you exactly how the underlying storage engine and the data model directly dictate what each database is actually good at. Look at PostgreSQL on MySQL. Both rock a B-tree engine and both are relational. This makes them the undisputed champions for complex queries, strong ACID guarantees, and read-heavy applications. Then look at MongoDB, utilizing a similar B-tree structure but paired with a document model, perfectly positioning it for evolving schemas. Move down to Cassandra, an LSM-Tree engine paired with a wide column model, built entirely for massive write throughput at a global scale. Redis strips away the disk entirely for an in-memory key-value model, absolutely dominating sub-millisecond caching. And finally, DynamoDB leverages LSM-Tree concepts to provide unparalleled availability at massive scale. This isn't marketing fluff, folks. This is physics and computer science dictating real-world use cases.
Section 5, the 5-question framework. With our map in hand, let's walk through a concrete framework you can use to confidently choose your next database.
Before you write a single line of code, you need to ask yourself these 5 strict questions. First, how structured is your data? If it's fixed with clear relationships, go relational. If it's highly variable, consider a document store. Second, what's your read-to-write ratio? Heavy reads? B-tree engine. Massive, continuous writes? You need an LSM-Tree. Third, how strong do your consistency guarantees really need to be? Handling financial data? Strict ACID. Just need high availability for a social feed? Look at eventual consistency. Fourth, and this is a big one, what is your realistic scale? Do you actually need sharding? And fifth, do you need sub-millisecond access for hot data? If yes, consider putting an in-memory layer like Redis in front of your primary database, rather than trying to force a disk-based database to do something it wasn't designed for.
I want to pause here because this point is absolutely crucial. Be extremely careful not to fall into the trap of resume-driven development. The most common mistake engineers make is reaching for a trendy, horizontally scaled NoSQL database just because some massive tech giant uses it. Listen, unless you genuinely have their specific scale, their team size, and their operational maturity, you are just inheriting their massive trade-offs without reaping any of the benefits. A single, well-tuned Postgres instance can handle vastly more scale than most developers expect. Start with a mature relational database and only reach for trendy horizontal scaling when you have the actual metrics to prove you need it.
And with that, we conclude our deep dive into database internals. Thank you so much to everyone who followed along for this entire 6-episode journey. We've built an incredible mental model together, moving from the lowest level disk pages all the way up to distributed cluster architectures. As we gear up for our next major explainer series on networking internals, I want to leave you with one final provocative thought. When you sit down to architect your next system, will you build for the scale you actually have or the hype you've heard?